Hi, I'm Youngjun Zhang from Seoul National University. In this work, we propose Villa, learning to act robustly with view-invariant latent actions. The motivation is viewpoint robustness in vision-based robot control. Many visual motor policies work well when the camera is fixed, but even small camera viewpoint changes can significantly degrade performance. This is especially problematic in real-world deployment, where camera placement can be rarely identical to the training setup. Most previous methods address this by learning view-invariant scene-level visual representations, but for control, making the entire scene representation invariant may be unnecessarily difficult. A scene feature contains static background, object appearance, layout, and test-relevant motion altogether. Our key idea is to enforce invariance on the dynamics rather than on the whole scene. In short, online latent action, not whole scenes. Villa learns a latent action that represents the transition between observations. Because this latent action captures how the robot and object moves, it focuses on action-relevant change instead of static appearance. This makes it a natural space for learning viewpoint invariant control representations. Our method had two stages. First, we learn latent actions from multi-view trajectories, and an inverse dynamics model predict the latent action from the current and future observation, and the forward dynamics model uses that latent action to predict the future. So this encourages the latent action to encode the underlying transition dynamics. Then we align latent action across camera views using ground truth action sequences. If two transitions have similar action sequences, their latent action should also be close, even if the observation come from different viewpoints. So we implement this with an action-guided weighted contrastive loss, together with a structural similarity loss that matches the geometry of the latent action space to the geometry of the real action space. Second, we train a latent behavior cloning policy. So this policy predicts the latent action from the current observation alone. So at the test time, we do not need feature frames. The predicted latent action is used to condition the downstream visual motor policy for raw action prediction. We evaluate Villa in both simulation and the real world. So in simulation, we use multiple manipulation tests and evaluate generalization from seen camera views to unseen camera views. So Villa consistently improves unseen view success compared to vanilla encoders or augmentation baselines, to scene level contrastive learning, and camera condition policies. As the viewpoint gap becomes larger, Villa also degrades more gracefully than the baselines. So in the real world SO-arm pick and place test, so Villa achieves 63.3% average success on novel camera views. So this is much higher than vanilla division policy and class, and also higher than recent baselines such as Pi 0.5 and small VLA. This suggests that even strong vision language action models can remain brittle under camera variation, and explicit view-invariant dynamics learning is still useful. We also evaluate unseen task adaptation. When pre-trained on text-free task can adapt to the coffee task with limited demonstration, Villa learns faster and reaches higher success than the baselines. This suggests that the representation is not only view robust but also useful as a transport dynamics prior. Finally, our representation analysis shows that Villa has high view entropy and low action entropy. In other words, features are well mixed across camera views while still preserving action relevant structure. So, to summarize, Villa learns view-invariant latent actions by aligning dynamics across camera views with action-guided supervision across simulation and real-world experiments. This improves unseen view generalization, outperforms VLA baselines under camera shifts, and enables better task adaptation. So thank you for listening.